Okay, this is Physics 102, Chapter 1 homework. It says an alpha particle has a charge of 2e. It's sent at a high speed toward a gold nucleus at charge of 79e. What is the electrical force acting on the alpha particle when it's 2 times 10 to the minus 14 meters from the gold nucleus? So we have this gold nucleus, and this alpha particle is over here, and it sort of zooms around like this. And we want to know when it's at its closest point, which is right here, we'll say. This distance is 2 times 10 to the minus 14 meters. We want to know what is the force acting on these. Now they're both positive particles, so we know that the force is going to be repulsive like this, but we just really want to know the magnitude of the force. So it's a fairly simple Coulomb's law problem. Coulomb's law is F equals K Q1 Q2 over R squared. This is our R value. Q1 is equal to 2e. Q2 is 79e. It doesn't really matter what you pick for Q1 and Q2, just as long as you get 2e and 79e. And then, of course, K is Coulomb's constant. That's 9 times 10 to the 9th, and that is in newtons meter squared or Coulomb squared. So I can put in my values here. K is 9 times 10 to the 9th. Q1 is 2 times E. That's 2 times 1.6 times 10 to the minus 19 coulombs. E is the fundamental unit of charge. That's on your equation sheet, but you should probably know it. It's the charge of a proton, or the magnitude of a charge of an electron. 79 is 79 times 1.6 times 10 to the minus 19 coulombs. That's the charge of a gold nucleus. 79 protons divided by R squared, which is 2 times 10 to the minus 14 meters, and that's squared. Alright, so that gives me I get 91 newtons. 91 newtons that is acting on both of these particles, actually. 91 newtons. Alright, 3 charges are arranged as shown in this figure. Find the magnitude and the direction of the electrostatic force on Q1, the 6 nanocoulomb charge. First thing we want to do is just draw our vectors that are acting on Q1. You know, this problem is almost identical to one that we had done before, but instead before we were dealing with gravitational forces, and now we're just dealing with electronic forces. The importance of this is that we're dealing with vectors, and when you deal with vectors, you have to know how to add up vectors and figure out what is the resultant vector. So anytime you're dealing with vector quantities, you need to be able to do this type of calculation. And if you're taking standardized tests, it's very common that you'll have some type of vector problem on it. So let's just draw all the forces that are acting on Q1. We have the force due to particle 2. I'm going to call this F12. It's a repulsive force because they're both positive charges. And then we also have F13, which is this force. F13, and notice that it's attractive because this charge is negative, and opposite charges are going to attract. Now, I need to figure out a couple things just about the geometry. If I draw my coordinate system here, I need to figure out what is this angle. I'll call it theta. Well, let's draw a little triangle. This is going to be my triangle that my charges are located on. This side is 5 meters. This side is 2 meters. My coordinate system, my x-axis, comes over here. So this is my angle theta. I want to figure out what is this angle. I'm going to call it phi. So in order to find phi, I say the inverse tan of SOHCAHTOA, T-O-A. Tan is opposite over adjacent. So the inverse tan of opposite over adjacent sides, that is, the opposite side is 5. The adjacent side is 2. The inverse tangent of 5 over 2 is 68 degrees. So that tells me that this angle is 68 degrees, and so this angle is 90 minus 68, or 22 degrees. So theta here is 22 degrees. That's the angle for F13 from the positive x-axis. We're also going to need to know the distance between particles 1 and 3. So let's just go ahead and do that. Again, I have a triangle that looks like this. This is 2. This is 5. I'm going to call this side R13. And I can figure out what is R13 is just the square root of 5 squared plus 2 squared. That's from the Pythagorean theorem. And that's equal to 5.4 meters. Alright, so that's just some of the geometry, and we'll use those values as we move along. Now next, let's find the magnitudes of the forces. The magnitudes of the forces, and then we'll move into actually resolving the vectors. So first of all, F13, K, Q1, Q3 over R13 squared. So that's 9 times 10 to the 9th. I'm going to leave off the units just for sake of space. Q1 is 6 nanocoulombs. That's 6 times 10 to the minus 9 coulombs. Nano is negative 9. Nano sort of looks like 9. You know that nano is small, so it's negative 9. Q3 is 3 nanocoulombs. That's 3 times 10 to the minus 9. Notice that I don't put the sign here because I know the sign denotes a direction, and the direction has already been determined just by saying that opposite charges attract, like charges repel. Divided by R13, I've already figured out what the distance between particles 1 and 3 is. That's 5.4 meters. And then we want to square that value, 5.4 squared. That gives me a force of 5.6 times 10 to the minus 9 newtons. So that's F13. We also need to figure out what is F12. It's going to be K, Q1, Q2 over R12 squared. I'm not going to put in the values here, but just note that R12 is 2 meters. That's the distance between particle 1 and particle 2. And that gives me a value of 5.4 times 10 to the minus 8. Notice that F12 is a lot bigger than F13. And that comes about because of a couple of things. One, that Q2 is a little bit bigger than Q3, but more importantly, it comes about because the distance between Q1, that is, distance between this particle and this particle, is a lot smaller. Well, not a lot, but almost a factor of 3 smaller than the distance between this particle and this particle. All right, and because the force has an inverse square relationship, that is, the force is proportional to 1 over the distance squared. If you make your distance bigger, it makes your force smaller at a pretty big rate. All right, so if you make your distance bigger by a factor of 2, it makes your force smaller by a factor of 4. All right, because of that inverse square relationship. We'll see that in the concept test, too. Okay, so there are magnitudes. Now let's just draw out these vectors. I'm going to put in values here. So I have F13. This is going to be 5.6 times 10 to the minus 9. And I want the y component, so it's times the sine of 22. And then this is going to be 5.6 times 10 to the minus 9 times cosine of 22 degrees. And then this is 5.4 times 10 to the minus 8. Now, I can tell already that my resultant vector is going to be right here. I can tell that because in the y direction, the negative vector is a lot bigger than the positive vector. The negative y vector is a lot bigger than the positive y vector. So it's going to dominate, and it's going to drive that final force vector that I'm looking for, the red line here, into the fourth quadrant. All right. So now I'm going to add up my y components. I'm going to add this number to this number. I'll write it out for you. I'll say 5.6 times 10 to the minus 9 times sine of 22 minus 5.4 times 10 to the minus 8. That's going to equal negative 5.2 times 10 to the minus 8. Alright, so when I draw my new force vectors, I'm going to have one here, 5.2 times 10 to the minus 8 newtons, and it's in the negative direction. And then this is going to be in the x direction, is 5.6 times 10 to the minus 9 times the cosine of 22, which is 5.2 times 10 to the minus 9. Now, again, I see that my resultant vector is going to be here. I want to know the magnitude of that vector, and then I want to know the angle. Let's call the angle, I don't know, gamma. All right, so I want to know that angle, and I want to know the magnitude of the vector. To find the magnitude of the net force, I say that it's the square root of 5.2 times 10 to the minus 9 squared plus 5.2 times 10 to the minus 8 squared. And the magnitude then is 5.2 times 10 to the minus 8. So that's the first part of the answer. And then I also want to find this angle gamma. Let's see, I'm running a little out of space over here. I'm going to do it over here on the side. So to find gamma, it's going to be the inverse tan of opposite over adjacent. That is, the opposite is 5.2 times 10 to the minus 8 over 5.2 times 10 to the minus 9. And that gives me an angle of 84 degrees below the positive x-axis. And that's the second part of the answer. The magnitude is 5.2 times 10 to the minus 8. The direction is 84 degrees below the positive x-axis. Right, an object with a net charge of 12 microcoulombs is placed in a uniform electric field of 610 newtons per coulomb, directed vertically. What is the mass of the object if it floats in the electric field and does have a positive negative charge? Let's just draw our force vectors. We have our weight of the object, and then we also, if it's floating, the electric force has to be equal and opposite the weight. So the magnitude of the electrical force has to equal the magnitude of the weight. So I can say the electrical force is QE. That's how we define what the electric field is, in fact. That is, we define the electric field based on this expression that F is equal to QE. All right. So the electrical force is given as the charge times the electric field, and of course FW is M times G. Now we're looking for the mass, so let's just solve this for mass. And then we just plug in some values. We have Q is 12 times 10 to the minus 6 coulombs. E is 610 over 9.8. Positive there because it's G. And then I've solved for mass. Let's see, my coulombs, I'm left with newtons over acceleration, force over acceleration, which is a mass. See, and I express this in grams, so I'm going to expand out this scientific notation. And I want to express it in grams. That means I need to move my decimal place over 3 places. So this is equal to 0.75 grams. So that's the mass. That's the first question. And does it have a positive or negative charge? A positive charge feels a force in the same direction as the electric field vector. So this force is in the same direction as the electric field, so the charge is positive. All right? If we had a scenario where the electric field was down and you had a charge that was floating like this one, so you have the same force vectors, this one would be a negative charge. All right, a proton is accelerated by a constant electric field of magnitude 1250 newtons per coulomb. Find the acceleration. Alright, it's a proton, so I know a couple other things. That is that Q is equal to 1.6 times 10 to the minus 19. That's the fundamental unit of charge, the charge of a proton. I also know the mass of a proton. This is on your equation sheet, but, you know, it's a useful number to know. Alright, we can do this first part. This is similar to what we've had before. The force due to the electric field from Newton's second law is equal to the mass times the acceleration. So the acceleration then is Fe over m. The electric force is QE over m, and I know all these values, so it's 1.6 times 10 to the minus 19 times 1250, which gives me units of newtons in the numerator, over mass, which is 1.67 times 10 to the minus 27 kilograms. So that's newtons over kilograms. Give me acceleration. And the acceleration then is 1.2 times 10 to the 11 meters per second squared. And that acceleration, by the way, it doesn't ask this, but it's in the same direction as the electric field. Now I also want to know what is V after a certain amount of time, and I know that V equals V naught plus AT. Because it's initially at rest, I can say V naught equals 0, so this is just simply plugging in 1.2 times 10 to the 11 times my time, which is 1 times 10 to the minus 8 seconds, gives me 1200 meters per second. Alright, don't forget to your other kinematics equation. You might see it as well in old test questions, or new test questions, where you have to find the distance that it travels in a certain amount of time. Alright, a styrofoam ball is covered with conducting paint, has a mass of 5 times 10 to the minus 3 kilograms, charge of 4 microcoulombs. What is the electric field directed upward that will produce an electric force on the ball that will balance its weight? So, electric field up. Here's our styrofoam ball. We know that the force due to the electric field is up because it has a positive charge. And then we also have the weight. So this is very similar to the previous problem that we worked, except here I want to know what is E. So Fe is equal to Fw. It's QE equals M times G. I'm solving for E here. The mass is given. G is 9.8. That gives us units of force in the numerator, charge in the denominator. Have to convert it to coulombs. Make sure you know your micro and nano especially. Right, 10 to the minus 6 and 10 to the minus 9 for nano. And that gives us 12,000 newtons per coulomb. Alright, this figure shows the electric field lines for 2-point charges. What is the ratio of Q1 to Q2? What are the signs of Q1 to Q2? In this case, you want to count the lines for part A. You have 1, 2, 3, 4, 5, 6, 7, 8 lines over here, and 1, 2, 3, 4 lines over here. The ratio of Q1 to Q2 is just the ratio of the number of lines. That is 8 over 4, which is 2. Q1 has twice the charge of Q2. Alright, because it has more field lines. It has more field lines, rather, because it has a bigger charge. So there's a greater electric field around Q1 than there is around Q2. Now, for the signs, need to remember that electric fields originate in positive charges and end at negative charges. So Q1 is positive and Q2 is negative. Test questions I've given in the past, let's say that Q1 has a magnitude of 10 microcoulombs, then what is Q2? For our example. Alright, and Q2, you know, has to be half the magnitude, so it has to be 5 microcoulombs, and it has to be negative because the field lines end there.